Just look at this, an Auric 1 acquired from eBay as untested, which we all know means tested but didn't work. We plugged this into our composite mod to go cable back in RetroRapid episode number 3, and we got a checkerboard. Not quite the retro magic I was hoping for. Today we'll be taking a closer look at the Auric and hopefully bringing this one back to life. Before we start probing chips, let's take a quick detour into the Auric story. The Auric 1 launched in 1983, created by Auric Products International, a spin-off from Tangerine Computer Systems, the same folks behind the Microtan 65. Back then, Britain's home computer scene was fierce. The ZX Spectrum, BBC Micro and Commodore 64 dominated store shelves. Auric tried to position itself in between, cheaper than the BBC, more polished than the Spectrum. It used a 1 MHz 6502A CPU, 16K or 48K RAM, and a vibrant colour display, at least when everything worked. A year later came the Auric Atmos, essentially the same machine but with a vastly improved keyboard and a ROM with bug fixes. Even the Atmos board still bore the silkscreen legend Auric 1, a reminder of how close these two were. One of the fixes, the notoriously unreliable tape loading routine. On the Auric 1, programs often crashed mid-load, something we'll probably see firsthand if we ever get this one fully running. Did you ever have to reload tapes a dozen times? And if so, did you have any tips on how to get them to load more reliably? Do drop them in the comments. It might help all of us Auric tinkerers out there. Despite its flaws, the Auric 1 sold around 160,000 units in its first year, impressive for a small British startup. The Atmos followed in 1984 at £129 for 48K, while the original Auric 1 was £99 for 16K and £169 for 48. And it was in France that Auric truly found fame, strong sales, local software, and even French exclusive releases. Competition from Amstrad CPC eventually ended production, but the Auric line left a real mark in 8-bit history. So let's take a closer look at our Auric here. Checkerboard screens usually point to trouble during reset. First thing to check is the power. The L7905 produces a -5 volts. Cleverly, the Auric designers swapped the ground and power rails so -5 became +5. Why? Cost efficiency. The 7905 was slightly cheaper than the 7805 that would have done the job directly. Classic 1980s savings. All major ICs, the ULA, 6502, 6522, memory and logic are getting a healthy 5 volts. Clock signals? Check. Everything's ticking. Next up, the reset circuit. Now most 6502 systems use a proper timing IC for power on reset, but Auric took a much simpler path, a resistor-capacitor network. As the capacitor charges through a resistor, the voltage rises exponentially, and once it crosses approximately 3 volts, logic reads as high and the CPU then begins execution. Simple, but fragile. Over the decades, electrolytics dry out and timing goes wonky. To test the theory, if I briefly short pin 1 and pin 40 on the 6502, it forces the reset low and it boots. There we go. So let's quickly test this capacitor. Well, it's not a dead short, but that's not an indicator it's still working. I think we'll replace it anyway. So replacing the 1 microfarad capacitor hasn't worked. So let's swap to a 10 microfarad capacitor. It will take slightly longer to charge. There we go. We have a much better, reliable reset. After reset, The screen looks all white. In the top right hand corner we should see the word caps, but we get CCPP. Interesting. Typing seems to work, but you can't see anything, and that suggests some sort of memory addressing problem, so time for a board inspection. Well, on inspection I can see IC21 has a leg folded under. I'll remove it, straighten it and socket it. It's probably not going to be the issue, as this would have come from the factory like that, but let's get it done anyway. Well, that's got it out. Let's test it before we reinstall. We passed this testing. Let's put it back in. Then I can see that C1 has its legs touching. Now, again, unlikely to be the issue. Unfortunately, I can't seem to show you a photo, but if I unsolder it and show you, there we go. But we can also see that this is now leaking. So the electrolytics definitely are going bad on this. Now, C1 is to do with the sound circuit, so these legs touching would have caused a nasty buzz, but wouldn't have stopped it booting. So let's replace all the electrolytics while we're here. Oh, by the way, this button underneath, it's not a reset button, although it's marked as that. It's actually an interrupt, a bit like the BBC Micro's escape key or run stop key on the Commodore. It asserts the NMI pin on the 6502. I spent far too long pressing that one before I thought to check the schematics. Has anyone else fallen for it? Next, onto the scope. Checking data and address lines, comparing them with the schematic. Well, D1 looks a little odd, so I've desoldered it and tested it and it looks fine. Apparently the memory ICs and the memory controller typically will be the things to go, so let's do the rest of them as well. That doesn't seem to have made any difference. I suspect I must have shorted two pins together when testing. That would have explained the strange reading on D1. The system responds to commands that I type blind, like zap, so let's try using paper and ink. Oh, we can now see the text. That's great, it's visible. But we can also see that every other character is doubled. Ready has become Ray. And that tells me that A0 is not toggling properly. If it were D0, we'd see completely wrong letters. But because we're seeing doubled letters, A0 must be stuck. The CPU is reading the same memory cell twice in the video memory. Doing A0 on the schematic, it runs through IC8 pins 5 and 6 as inputs and 7 as outputs. If I gently bend out pin 7 on IC8, it disables A0 entirely. Well, we've got a checkerboard crash, and that tells us something very important. It tells us that the CPU, the memory, and all the glue logic is working. Because if we disable A0 and it doesn't work, it must mean that it was working before we disabled it. So the only thing left is the ULA. The ULA is not asserting A0, so time to order a replacement. There's a vendor on Tindy in Bulgaria. Let's hope that the shipping times aren't too bad. Well, it's now 2 weeks later and the package from Bulgaria has arrived. So let's desolder the original ULA, drop in a socket and put in the new ULA. And success. It boots. So let's do the normal Hello World basic test. Perfect. This is where that button on the bottom comes in handy. Let's try loading a tape. It's working, and it's glorious. The Auric lives again. In part 2, I'll install a proper composite board so we can get a better picture, and we'll test out a few more tapes. Back in 2008, Mike Brown designed an Auric Diagnostics ROM and board. Now I've tried it several times, even when the Auric was fully working, and it always crashes the system. Has anyone else managed to get this board running reliably? And if so, let me know in the comments. I'd love to include it next time. Diagnostic boards are always a useful tool. So to recap, our untested Auric 1 had weak reset capacitors, a few tired electrolytics, and a failed ULA. We also learned firsthand how cost-sensitive the Auric was when it came to design and QA, and along the way we learned how fragile RC timing can be. We traced A0 through the schematic and revived another slice of retro history. I've also added new rubber feet. Not quite originals, but at least it stops the Auric skidding around on my desk. That's the charm of vintage repairs. Every fix teaches us something new. These machines may be 4 decades old, but they still reward patience and curiosity. So tell me, what's been your most satisfying retro repair? Do drop a comment in below, I will read them. And if you've enjoyed this deep dive, please do give it a like, share it with your retro loving friends, and subscribe so that you don't miss part 2, where I'll do a permanent composite mod and more tape tests. Thanks very much for watching. Until next time, keep those Auric pixels dancing. See ya.